Hey folks, this is Captain Jones here to talk to you about interrupts. We're going to separate this into two lessons. In this lesson, we are going to describe what interrupts are, what benefits they provide us, and we're going to compare them with this idea called polling that we looked at when we first looked at our input devices, our input-output devices. And today we're going to look at primarily the first step, which is how do we cause the interrupt to occur? In other words, what is what are the external circuitry that we need to sort of add to the processor to generate to allow for these interrupts to occur? So we're going to describe that circuitry, and we're going to describe the very slight changes we need to make to a couple of key status registers that are able to support those interrupts. And lastly, at the end of this lesson, you'll know when in the instruction cycle the LC3 is able to respond to interrupts. So let's get started. Okay, so here you can see a couple examples of polling for our hardware devices. I think the one that I liked to use in the lessons on memory mapped input and output looked like this. So this is an example of checking the status register, in this case the keyboard status register, to see if there's a new value. If there is, great, we load it, we do something with it. And if there isn't, and otherwise we sort of move on to some other code. And the assumption is that at some point down at the bottom here, we're going to branch back to the top and check again. But like I kind of teased in that first lesson on memory mapped input, the question we might ask ourselves is, okay, well, what happens if keyboard data arrives while we're doing other processing? Maybe there's lots of other code down here, typists, don't run as fast as computers, but they don't run super slow. So, what happens if how do we respond to keyboard data if there's other stuff we need to do? An updated or a slightly different version, the one that books like to use, tries to solve one problem, creates another one where, we say, okay, we're going to, instead of doing other stuff while we're waiting for keyboard data, we're just going to spin. So we're going to read the status register, and as long as there's no new data, we're just going to jump back and we're going to read the status register again. So we're going to execute these two instructions over and over and over again until there's some value in the status register. So then we'll do something with our keyboard data, and if we want, finally other code gets to run. And when that's finished, we come back to the top to try to read the keyboard again. This also, though, has problems. So we might be, here we might be very responsive to the keyboard, but, no other code gets to run. Literally the only thing our processor is doing when it reaches these two lines of code is waiting for somebody to type a key on the keyboard, which is, not only inefficient, but it's just not scalable. If the keyboardists, if they type sort of their last value and we're still here waiting for the next one, then our processor might just be doing nothing until it's waiting for the keyboardist to type a key, which is just not going to work. What we want is something that kind of looks like this. This is an example of how an interrupt might work, where we are executing a program, and then boom, right after instruction n+2, our processor is somehow made aware of the fact that there is new data in the keyboard. And so the processor sort of puts program A on pause. It does whatever it needs to do with that new piece of keyboard data, and once it's finished, it sort of brings program A back into focus. And program A is hopefully none the wiser, other than there being some amount of time that occurred between these two instructions. The processor is in the exact same place as when it executed, and the instruction n+2 is n+3. And so what this lets us do is potentially write program A to do stuff. We can write programs to our computer that allow it to work on other things while it's waiting for data from a hardware device, and it can do kind of the two things at the same time. The only catch is that this requires that the hardware device be able to sort of alert the processor of its status that's outside the normal execution cycle. We can't use our normal instructions here to try to read that data, because then we run into these two problems where it's not synchronized. So interrupts are the way that we're able to do that, and it's going to require kind of two things. It's going to require a hardware solution and some software solution. So we're going to look at the hardware solution today. You can see in this diagram here or at least in the upper left-hand corner here is sort of our keyboard peripheral, if you will. We've got our keyboard data register connected to our keyboard status register. This is the memory mapped input device that we know and love. But we're going to provide some external circuitry now that potentially provide this signal to the processor that the keyboard has new data. And so the first change we're going to do is we're going to extend the status register. We're going to add some significance to bit 14 here. Bit 15, if you recall, was the new bit. This is the bit that got set when there was new data in the data register. And IE here stands for interrupt enable. So we don't necessarily want every device to interrupt the processor whenever they want. We're going to control that. So we're going to say as long as there is data to be read and the keyboard is allowed to interrupt the processor, the interrupts are enabled on the keyboard, then we got a little AND gate here to sort of AND those two signals. Then we generate this signal, which is effectively says, hey, there's a device that needs processing. So down here we got a little running list of what do we need to do to handle an interrupt. Number one, the device has to want an interrupt, so that's represented by this new bit. The device has to have the right to request an interrupt. That's interrupt enable. So if the device here, the keyboard, is wanting and able to request an interrupt, this signal says, hey, we need some service. That's going to go into an encoder here with potentially other input devices that are all asking for interrupt requests. And the reason it's an encoder is because what we want to do is separate these input devices by priority. The keyboard might be trying to alert the processor to the fact that there's new data in the data register, but there might be a separate input device that's monitoring our power levels that notices someone just yanked out the power cord that needs to alert the processor to, hey, save the data, save everything, we're about to get shut down. And that clearly should run at a higher priority level. The processor should be alerted to that before it's alerted to the fact that there's new data coming in from the keyboard. So this is an encoder here. Takes all the devices that are requesting interrupts, and in the highest priority one is what gets put here. In this case, there are 3 bits because on the LC3 we're allowed anywhere from 0 to 7 priority levels. And so this starts to explain this little bit in the processor status register. Recall from one of our earlier lessons that we talked about the condition codes, we talked about the privilege level. We didn't mention these bits in the middle here that are very important now for this lesson. These bits in the middle that happen to be in positions 10, 9, 8, so bits 10, 9, 8 in the processor status register are the current priority level of whatever program is running on the LC3 at this point in time. And if it happens that the priority of some hardware device requesting service is higher than the priority of whatever's currently running, then we potentially have the need to run this program. You typically user programs run at a very low priority level. So in this case, if we were doing other stuff, we might have the user program at a 0 or 1 priority level. And the keyboard at a slightly higher priority level. The text actually mentions that it's sort of hard-coded to priority level 4. And you might imagine that in the example I gave before, the input device that's monitoring the power supply is at a priority level 6 or 7. So in that way, if a user program is running and the keyboard says, hey, there's new data, then the new data on the keyboard operates at a higher priority. Maybe the processor sort of starts running that code, so then the current priority would be a 4 because that's coming from the keyboard. And then as soon as the the input device that's monitoring the voltage level sees that someone yanked the power cord out, then the processor says, oh, shoot, priority level 7, that's higher than 4, so I'm going to switch to this code that will run if I lose power. So this box here is testing if the priority of the device needing service is higher than that we're currently running. So, condition number 3 that we need to have in place is that interrupt be more urgent than our current program. In other words, that it have a higher priority level. And then lastly, we need to make sure that this GIE bit is set, which stands for Global Interrupts Enabled. So just like we sort of enabled the interrupts in the keyboard status register, and we can turn that off. We need to we have the ability to turn interrupts on and off in the LC3 globally. So this bit here will sort of turn off all interrupts or turn on or allow all interrupts to run in the processor, and this is in bit position 14. So then the last thing we need to do is check and make sure this is set. If this is 01 and we have a device requesting service which has a higher priority than our current device, then we generate this interrupt signal, and that's what alerts the processor to the fact that it needs to switch, to running some other code to be able to handle new data on the keyboard, or the fact that someone pulled the plug out. So our last condition here is that interrupts are enabled globally. If all four of these conditions are met, as represented by this circuitry here, then our processor can execute this interrupt. So if that interrupt is a 1, so if all these conditions are met and there's a device that needs servicing, then we're going to configure our instruction cycle so that those interrupts are handled at the very top of the instruction cycle, right here in this very first bubble, where we might normally update the program counter and get our next instruction out of memory. As long as there are no interrupts, we'll execute the instruction cycle normally, but if this interrupt is equal to a 1, then instead of sort of using our normal instruction flow, we'll move to this bubble here to actually process that interrupt. And we'll look in a future lesson what sort of that flow, that instruction cycle looks like. The key thing to remember here is that interrupts, if the processor, if the LC3 is in the middle of executing like an add instruction, it will not immediately go to the interrupt. The LC3 is set up so that add instruction or whatever is executing at that moment will sort of finish, and then right when the processor is about to move on to the next instruction, that's the moment when, if there's a pending interrupt, it'll start processing that. And the reason is just because there's a lot of work that goes into allowing the processor to run this interrupt and to come back to its place in the program wherever it was right before it starts processing that interrupt. If we were to try to do that in the middle of these, somewhere in the middle of this instruction cycle, the process of trying to get back to the exact same spot would be way too complicated. So as a means of simplification, the designers of this processor said, okay, we're just going to make the simplifying, restriction that we will allow whatever instruction is currently executing to finish, and then at the top of our instruction cycle, we'll process our interrupts here. And getting back to this location is much easier than getting back to somewhere in the middle of our instruction cycle. Okay, so the last thing to kind of note here is just that this means our architecture diagram is slightly updated. Previously we had arrows coming from our control unit that sort of went one way, looked like, to our elements in the computer here. But now to implement interrupts, our inputs and our output devices also are sort of providing signals back to the control unit. Okay, so today we looked at interrupts. We identified a couple problems with polling our output, our hardware devices, and we sort of described, well, ideally we had this solution where I can have a program that's running on the LC3, and then something else separately from that can alert the processor when there's new data in the keyboard data register, or when someone's yanked the plug on the processor. Doing that requires sort of operating outside the normal instruction cycle, so we had to add a little bit of circuitry to our LC3 to be able to do that. There were 4 things that needed to happen in order for our processor to handle interrupts. There has to be a device that wants an interrupt. So in the case of the keyboard status register, we used the new bit to indicate that it needs servicing. We added the interrupt enable bit in position 14 for the status register to say that the device has to have the right to request an interrupt. So this bit needs to be set in order for the keyboard to be able to request an interrupt. Number 3, the interrupt has to have a higher priority than the currently running program and any other interrupt requests that are pending. So we have this priority encoder that will sort of output the highest value of whatever IO device is needing service, and as long as that value is larger than the current priority level, then we can identify that there's an interrupt that needs servicing. And lastly, the last thing that needs to happen before our processor is alerted to this interrupt is that number 4, interrupts have to be enabled globally. So this bit 14 in the processor status register global interrupt enable has to be set. And if that is all true, then we generate this interrupt signal. And at the start of the next instruction cycle, whatever that is, we start processing our interrupts. All right, in the future lesson, we'll look at how this effectively this flowchart goes, how we handle these interrupts in software. But for today, That's all I got. I'll see you next time.